Let's look at kind of a less fun one, meaning to say that it's a lot less expensive to generate. But it gives some intuitive, it helps us develop intuition. So this is going to be what we call example 2.3.3. One of the problems that we will be studying in this class is how to visualize or interpret visually what's going on with a vector operation. So what we're going to do is we're going to define some vectors. We're going to let x be equal to 2, 1. So how big is that vector? It's a 2 by 1 vector. And let's graph it. Quote unquote, graph this vector. Could you guess how you graph a vector? Not quite. This is where I get really upset with physicists because they say all things have to be direction and magnitude. But the problem with that is if I collect, so for example, let's imagine that I put 15 masses and 16 springs. How big would my displacement vector be? How many different displacements would I have in that system? 15. Okay, now visualize a 15 by 1. Give me the direction of that thing. It's very, very hard, right? Formally speaking, from the context of linear algebra, I don't think vectors are directions and magnitudes. I think vectors are storing scalar valued either by rows or by columns. So formally speaking, the word advector is Latin, and it means carrier. So rats used to be carriers of diseases. That's why they call it vector control, because you're controlling carriers, right? When I think about linear algebra and I'm thinking about vectors, they are carrying information. What type of information do they carry if they're real valued entries? Yeah, so in the real world problems, they carry measurable data, but formally speaking, they just carry a bunch of different scalar valued entries. So if it's an n by 1 vector, it's carrying n different scalars. If we would like, once we have that information, we can impose geometry on top of it, aka we can use the physical world, like in physics, to try to understand what vectors represent in terms of forces and accelerations and displacement. But strictly speaking, I don't need that visualization to be able to store information. And in this class, I want to separate the two of them because you ever heard of big data, machine learning, AI, all that stuff? Well, formally speaking, you're going to have data sets that are in the tens, if not hundreds, if not hundreds of thousands, if not millions. How do you visualize that?
You don't.
Well, you can, but you have to impose visualization techniques on top of that. You can't just say, oh, it's magnitude and directions. You have to say, well, what does it actually mean to be a magnitude? What does it mean to visualize that thing? So formally speaking, in this class, I'm going to step away from thinking of a vector as magnitude and direction, unless I need it in the physical space. And I want to say a vector is a carrier information. So it's literally just a set of scalars organized into either rows, aka it's a column vector, or columns, aka it's a row vector. So in this case, we can impose the idea of magnitude and direction, but more specifically, let's go ahead and look at, so if you look at 2, 1, what's the first coordinate?
2, blank.
2. Okay, so we would go 2 over and 1 up. Let's call this the vector. So we'll call that dot. We're going to call it the vector. There's no connection between that dot and 0, right? Okay, let me ask you this. What would x0 be? And by x0, we're just going to call that 0 times x. What is that? 0, 0. Okay, so now this is my x vector. Here's my x0 vector. Did you have a question, Joe?
Kind of. Maybe I'll just wait.
Okay. All right, what would x negative 1 be? So let's go x negative 1. Could you guess what that is? Negative 1 times x. So it would be negative 1 times 2, which is negative 2. Negative 1 times 1, which is negative 1. What's that one? Yeah, so now it's over here. Okay, let's do another one. What would x2 be? Okay, so now this thing would go all the way up to 4. So this would be x2. Could you guess what x negative 2 is? Now let's forget about the pattern forget about the actual calculation. What's the pattern? If I scale it by 2, I take this thing and I move it 1 more the distance, right? If I scale it by negative 1, I literally go the opposite. What if I scale it by negative 2? Opposite. So now I can impose geometry. What if I scale it by 1/2? So this would be now negative 4, negative 2. What about x, I don't know, positive or negative 1/2? Do you have a preference? Positive 1/2? What's that? 1 comma 1/2. Okay. What are you noticing? Oh, that's actually, so that line that you just called is called the span. And in Math 1C, we saw this. It's called the direction of x. That was one of the major takeaways from Math 1C, right? So we're going to call this later, we're going to call it the span of the vector x. And the span of x is the set of all a times x such that, can you guess what condition we have? A is any scalar. In Math 1C, we used to call this the direction of x. It was a generalization of what it meant to be directions. So what does scalar multiplication do in terms of a geometric interpretation of a vector? And I don't want to think about a vector as a magnitude and a direction. Do you notice that if we just think about this as a dot, there's no magnitude there?
It's a line.
What is, no, but what is scalar vector multiplication? I agree with you, if you do all scalar vector multiplication, you produce a line. But if you do a single scalar vector multiplication, what are you doing? You get a point, and what do? I really like this, actually. We're going to come over here, and then we'll end today's lesson. So we can interpret geometrically, and we're going to do this for the rest of the quarter. We can interpret scalar vector multiplication geometrically to achieve 2 goals. What are the goals? Yeah, but think about what's happening here. So like, what did we do when we multiplied by 2? What did it do? So we started here, and then what did we do? So if you looked at this length versus that length, it would have doubled it. What do we do when we multiply by 1/2? Halved it. What if we multiplied by 4? Quadrupled it. So what are you doing when you multiplied by some magnitude? You're stretching it or you're making it shorter. So one goal would be to stretch or compress original length by some scalar, right? What's another thing we do? Rotate. So multiplication, and you can actually think about real valued multiplication in this center, right? Real valued multiplication either stretches, compresses, or stays the same. What's the only number that keeps the magnitude the same? The number 1. That's the only one out of all the ones that are possible that doesn't change the value. Or I guess you could say negative 1 doesn't change the value, but what does negative 1 do? Rotate. So the other thing that scalar vector multiplication does is that it rotates. And we're going to see that this is the same thing that happens in inner products. It's the same thing that happens in matrix vector multiplication. So this rotates the vector. And in this one, it's the least interesting rotation, either no rotation or what? Yeah. So, or 180-degree flip. I call that opposite orientation.